There sure are a lot of stars up there, and they are really very, very far away, and far apart from each other. What do you think is in between them, Velocity?
Void. Nothing. Nothing but space.
Actually, that void may be totally full, with dark energy. Something we cannot see, detect, or measure.
Something we can't see, can't detect, can't measure? Are you sure we're not talking about your brain, Herc?
Ha ha ha, very funny. No, I'm talking about dark energy and dark matter. Scientists think that maybe 80% of the universe is made of it. It is one of the most fantastic mysteries of the cosmos. Let's Explore Astronomy is sponsored in part by... Hey, give a shout out to our sponsors, without whom we would not be here. Visit their websites and partake of their services and products. A big thank you to the Yukon Department of Tourism and Culture and Westmark Hotels, Westmark Whitehorse. In 1917, Albert Einstein was puzzled. The universe is held together by gravity. But then, why does not gravity pull everything together? Einstein thought the universe was static, neither expanding nor contracting. So he figured there must be an opposite force on gravity, which he called the cosmological constant.
Then in 1929, astronomer Edwin Hubble discovered something that made Einstein change his mind.
Hubble discovered that the universe was expanding, and that the galaxies were moving away from each other. If the universe is expanding, then it meant that at one time the universe must have been a very small place, and some sort of massive explosion or Big Bang started it to fly apart.
Thus the Big Bang theory was born. About 14 billion years ago, the universe was born in a gigantic explosion. Dust and gas flew out everywhere, and soon gravity started making stars, galaxies, and planets.
Einstein's cosmological constant was thrown out. Gravity does not have a force against it after all. Eventually, gravity will slow down the universe's expanding, and then...
Oh my! Then the opposite happens. Throw a ball into the air. At first, it goes up fighting gravity, but soon gravity takes over and back down it comes. If the universe was expanding, it was like the ball going up. But soon
it would reverse and then collapse back on itself. The universe would end in the Big Crunch.
Then what? Maybe there would be another Big Bang and the whole thing would start again. Maybe this has happened over and over and over again for billions upon billions upon billions of years.
But then, in the 1990s, we discovered the universe as we know it is not the universe as we know it.
The universe was not slowing down its expansion. It was speeding up. This rocked the world of astronomy. How? Why? What's going on?
Astronomers everywhere started looking into this. Even the Hubble Space Telescope was called into action to investigate. The key was type 1a supernovae. Supernovas all create the same amount of light. The further away the supernova is from us, the dimmer the light. Now add in redshift. As an object moves away from us, there is a shift in the red color of the spectrum. The red light waves get longer. By putting together the data of how far away the supernova is and how much redshift there is, we know where the supernova is and how fast it is moving.
The Hubble telescope, along with ground-based and other space observatories, verified it. The universe is expanding faster now than ever before.
There must be an energy force overpowering the gravity. It was named dark energy. Maybe Einstein was right all along.
So if the universe is filled with dark energy, there must be dark matter that produces it. What is it?
One idea are MACHOs, which stands for Massive Compact Halo Objects. These are black holes, neutron stars, and brown dwarfs, but they do not occur in the universe in enough numbers to account for the dark energy required to expand the universe. Another idea are WIMPs, or weakly interacting massive particles. These are quantum particles like neutrinos, axions, and neutralinos. These would have been in abundance right after the Big Bang. But neutrinos do not have enough mass to create dark energy. But axions and neutralinos may. But they are just theoretical quantum particles. Do they even exist? The search continues.
Quantum physics tell us that these particles pass right through most matter, but when they hit each other, they annihilate each other. Could that create dark energy? The Fermi Gamma Ray Space Telescope has been searching for this. So far, certain WIMPs have been eliminated as dark matter candidates. The search continues.
So how much dark energy and matter is in the universe? The WMAP Space Telescope can read the background microwave radiation produced just 380,000 years after the Big Bang. This is what it looks like. So here is a timeline of the universe. We have not been able to see beyond the 370,000 years after the Big Bang mark yet. The first stars formed around 400 million years after the Big Bang, then the galaxies and so forth. Recently, the expansion of the universe has accelerated. And when we measure it all up, dark energy is 74% of the universe. Dark matter is 22%. And everything that we can see, feel, touch is only 4% of the entire universe. Is it machos? Wimps? Are the laws of gravity how we know them wrong? Or is it something else going on? It is the biggest mystery in the universe.
So what's going to happen to the universe? Will the dark energy disappear and gravity take over and the big crunch happens? Will dark energy and gravity balance out and the expanding stop and the universe slowly fades into a dark cold state called the big chill? Or will the expansion continue to speed up more until everything is torn apart? Every galaxy, every planet, every molecule, every atom ripped apart in the big rip? Whatever happens, that'll be tens of billions of years away. In the meantime, we continue to search for the answers to unlock the great mysteries of the cosmos.
Wow.
Check out our other episodes and let's explore astronomy series at www.tedcookproductions.com/LEA.
You will find all kinds of cool astronomy topics there.